For the sake of time, I'm going to give you about another 30 seconds.
Moses, what you think, Moses?
Oh, what I normally do when I see these kind of groups attached, whether they're withdrawing or donating, I usually draw their resonance structures and then go from there to see which has aromaticity and which one doesn't.
Nice. That's what I would do too.
Yeah, I think once you do the resonance structures, it does make it a lot more clear which one will have a more stable pi system and which ones won't.
So did either of you do the resonance structures for either one of these?
Yes, I think I drew them right on my paper.
Alex, did you do them right?
Let's see. Are they gonna be what's the word? Are they not conjugated? What's the okay? Can
I'm talking about the big A word.
the types of dienes, there's conjugated, isolated, and
Accumulated.
Accumulated. There we go. Sorry, I messed up my notes. And yeah, so on are we looking at like it's gonna be like this? Because we can't put another one right here.
Well, I guess one thing that we want to look at right here is when you see a ring system kind of like this and a whole bunch of conjugated double bonds like that, what should you be thinking?
These are electrons?
Well, they are electrons, but in the last lecture, what did we go over?
Last lecture. Not Deal's older, right? No.
No, this is from chapter 16.
No, I don't know what you're looking for. I'm sorry.
So, Moses, do you want to help her out?
Well, if I remember correctly, I believe we're going over aromatic structures that could either have ions or could have non-carbon atoms.
Ions or non-carbon.
Yeah. So Alex, do you remember aromaticity?
Aromaticity, yep.
Yeah. So basically, so while the question doesn't really say anything about it, and you can keep the structure there because we're going to be drawing on that.
Mm-hmm.
But while the question doesn't say anything about aromaticity, it's asking which one has the most stable pi system. And so the things that have to do with stable pi systems have to do with conjugated systems and what affects conjugation. Or in this case, whenever there's a ring and, because these are both rings and because they're both conjugated, what do we want to check for?
Extra stability.
From what?
The aromaticity.
Yeah. So if we see a ring that's conjugated, we want to check and see if it's aromatic.
Mm-hmm.
And so that's basically what we're gonna be doing is we're gonna be checking out the resonance structures on these two guys, and then saying, okay, well, is that gonna give us an aromatic system, a non-aromatic system, or an anti-aromatic system?
Mm-hmm.
Right. So what are the rules for aromaticity?
It's like the 2n plus 2.
Yeah, that's one of them. What do we call that rule?
That rule is called... it's not the endo rule, is it? No.
No, that would be for Diels-Alder.
Diels-Alder, right. Okay, yes, that makes sense.
It starts with an H.
Starts with an H. Oh, Huckel's rule?
Yeah.
Oh, cool.
And when is it anti-aromatic?
When it's just 2n.
2n?
Mm-hmm. Or it's 4n?
Yeah.
4n. Okay, cool. 4n.
And then what are the other rules?
Oh, the other rules.
There's a couple other.
For aromaticity. Planar. If it's planar when it's aromatic, it's going to be stable.
Mm-hmm. Well, it has to be planar or almost planar to be aromatic.
Mm-hmm.
Is it planar or planar?
Planar.
AR.
And then there's really one more, but we kind of already touched on it.
Isn't it just it needs to be a cyclic compound with some conjugated bonds?
Yeah, so fully conjugated cyclic compound. So what we're going to do for each of these guys is we're going to check and see what qualifications they have for these different things. And then if they don't follow under, so if they don't fall in line with the aromatic or anti-aromatic, what the heck? There we go. If they don't fall in line for the aromatic or anti-aromatic rules, then what do we call them?
Non-aromatic?
Yeah, non-aromatic. So otherwise, and Moses said that we want to analyze the resonance structures, right? So what's probably the first resonance structure we would want to do? I'll set it up really quick. So So what can we say about this ring right now?
Ring. It is conjugated.
Is it fully conjugated?
No.
Yeah, so it's not fully conjugated, not yet. That's why we do the resonance structure to see if any of the resonance structures are fully conjugated. But then does it fall in line with Huckel's rule?
Huckel's rule. Honestly, I don't really understand that rule. Could you show how it applies here?
Yeah, sure. So Huckel's rule, when it's talking about the 4n plus 2, it's talking about how many electrons are in the pi system. So if we look at something like this, the pi system is going to be basically this system of pi bonds that results from these double bonds. And so we want to say, okay, well, how many electrons are in those double bonds, or in the pi orbitals of the double bonds? And so since each double bond has 2 electrons in the pi part, it's going to be 2 electrons for that one, and then 2 electrons for that one. And so 2 plus 2 equals 4. And so that would line with 4n. So in this case, this guy is anti-aromatic because it has 4n. But then if we have something like this, like benzene, this one has 2, 4, 6 pi electrons. And so that's going to be 4 times 1 plus 2 equals 6. And then because benzene falls in line with all of the other rules, it's aromatic. Does that kind of make sense?
Hold on. 4 times 1 plus 2 equals 6. Where does the 1 come from?
So this is basically what we want to do is we just want to say, oh well, there's 6 pi electrons because there's 2 in each pi part of the double bond.
Okay.
And then so we know that there's 6, so we want to figure out, is that part of the 4n rule or the 4n plus 2 rule? And so what we have to do, so the 1 is only there, it's just an integer that you would multiply by 4 to get it to work to 6, if that makes sense.
Okay, so you start with your answer and then you see which of the formulas will fill it out.
Yeah, basically. Start with how many electrons there are and then see which formula applies to it.
Okay, so for the one that we're working on right now, the number is going to be 6.
Yeah, so there's 6. So does that mean that it's we know that it's not aromatic right now, right?
Mm-hmm.
But so it's not fully conjugated, but we know that there could be 6 electrons in it. Mm-hmm. So it could potentially be aromatic. Does that kind of make sense?
Kind of.
And so we have to do the resonance structure. So do either of you want to draw a resonance structure that you think will contribute to an argument for it being aromatic or anti-aromatic?
I would like to pass this one on to Moses.
Because the annotate one where I can write on the screen, right?
Yeah.
Oh no. Well, we'll see what happens.
If you have a hard time drawing it, you could just tell me what to do.
Okay, yeah, I think I prefer that instead.
Okay, yeah, that's fine.
What I was thinking, since carbonyls I know are electron withdrawing, just draw the electrons from the double bond going to the oxygen.
Like that?
Yeah, so that way the oxygen has a negative charge and then the carbon attached has the positive charge.
Wait, oh, that was the hexagon. That was also a hexagon. Oh my gosh. There you go. So, Do you see what you did there, Alex?
This, I see it. Mm-hmm.
Okay. Do you understand it? Or
Yeah.
okay, cool. So so what does this do for us?
Well, we see in that at least with that particular resonance structure, we can see that the carbon now has an unhybridized p orbital, which allows it to hyperconjugate with the rest of the system.
Did you say hyperconjugate?
Like, I don't know if that's the right word to use.
It would just be conjugate.
Okay.
Yeah. So do you understand that, Alex, or?
Somewhat. We can just keep working through it.
Okay, cool. Yeah, so basically what Moses said is right. The reason why this helps us is because this positive charge allows the entire ring system to be conjugated. So now we could do resonance structures around this whole thing. One, two, three, four, five. I keep drawing hexagons. Oh my gosh. And so we can do resonance structures around this entire ring, and that means that it's fully conjugated. So now it fulfills this rule. And what about, so does it still fall in line with Huckel's rule? That's one of the big questions.
Yeah, it's still the same number of electrons we're rotating, so it has to, right?
Yeah, exactly. So can we say that it's aromatic or non-aromatic or anti-aromatic?
Aromatic or, well,
Yeah.
it has to be aromatic, right?
Yeah.
Yeah.
Good job. So that's pretty much what we want to do for the other one as well. So what do you think the resonance structure is going to be on this guy?
Same thing, put the electrons from that pi bond up to the O.
Yeah.
Yep.
So now what do we do?
Now, if we can rotate it around the ring.
Yeah, we can, now that this guy has a p orbital that's included in this whole pi system, we could do resonance structures around it. So we don't necessarily have to show all of the resonance structures. We can if we want, but it's not the biggest deal. We just have to show that it can do that, not necessarily show all of them. So so does it fall in, so is it fully conjugated? Oh, hey, Miziel.
What's up? What was the question?
So is this ring fully conjugated now?
Is it fully? I believe so.
Yeah, it's fully conjugated. You could do resonance structures around this whole thing, and you wouldn't violate any rules as long as you do them right. And then, is it planar?
Planar. Yeah.
Yeah, it's planar. I mean, you don't really get into anything unplanar until you get to around like cyclooctane or something like that. I forget. Okay. And then, does it follow Huckel's rule?
For the anti-aromatic?
Yeah. So it has 1, 2, so 2, 4 electrons. And so 4 times 1 equals 4. The 1 is in. And so we would call it anti-aromatic. So the question is, which one has a more stable pi system?
More stable. Probably we're going to go with the number 2.
Yeah. Exactly. So, so what you would say is 2 has the more stable pi system because it is aromatic. And the thing about this other one, so number 1, do you think that number 1 is going to stay anti-aromatic?
It has to, right?
It doesn't have to. It has the option between, so it has an option between either resonating this positive charge. It has the option of either resonating the positive charge or not resonating it.
Mm-hmm.
So if it resonates the positive charge, then it's going to be anti-aromatic. But if it doesn't, if the oxygen doesn't pull that electron towards itself and cause that resonance structure, then it's going to stay non-aromatic.
Mm-hmm.
And so in this case, this one has no special stability because it has the option, or does that kind of make sense, Alex?
Yeah, so it's either anti-aromatic, but it's going to prefer to be the non-aromatic.
Yeah. So if something has a choice between non-aromatic and aromatic, it's going to go with aromatic because then it gains special stability. But if you're choosing between non-aromatic and anti-aromatic, you're going to go with the non-aromatic because you have basically no special stability, but you have no special instability. So that's the thing about anti-aromatic is it has a special instability. Does that make sense?
It does. Okay. Okay, so I forgot my question, but I have another one, which is it has everything to do with aromaticity, and the size is it's not really a factor.
The size would only be a factor if they're both the same, if like they're both aromatic or something like that. Okay. Then the size would matter, but in this case it doesn't because there's such a big difference between aromatic stability and non-aromatic stability.
Okay. And to be anti-aromatic, it also has to be a conjugated cyclic compound?
Yeah. So basically anti-aromatic follows all the rules of aromatic except for Huckel's rule.
Okay.
Yeah.
Okay, cool.
So,
thank you.
Do you see the time remaining thing?
Yeah.
Yeah, so technically we only have 10 minutes left. I could just start a new meeting if you guys want afterwards, after the 10 minutes, because I want to go over a little bit more than what we have. Mm-hmm. But yeah, so when it comes to aromatic problems, that's pretty much the process you want to go through, is you want to just look at what's given to you and you want to decipher what the question is asking about it. So like in this case, it says, is it more stable? But in this next problem, it's going to ask, which one is more nucleophilic? And so let's go to that problem. And we have to interpret that in terms of aromaticity. So, so Misael, how do you feel about aromaticity?
I don't really know.
All right. Good, because that means that you can only go up, right?
These two?
Huh?
Well,
I mean,
that one is aromatic. The one on the left.
Well, I mean, just in general, which one? Or I guess, how do you feel about aromaticity in general? All right, so I think we have 7 minutes. We should be able to go over this one. I remember having a hard time with this question, but I got it right eventually. I just had to think about it a lot. So it's saying, which of the following heterocycles is a stronger nucleophile in SN2 reactions? Explain. So what do we do?
I mean, we could just define what a nucleophile is first and work from there.
Yeah, we could do that. So how do we define a nucleophile?
Something with a lot of electrons.
Yeah, that's a pretty good definition of one. So if we're operating in a mechanism, because that's really when we see or nucleophiles and electrophiles as in mechanisms, right?
Yeah.
So if we were operating in a mechanism, what would be, I guess, a distinguishing factor for a nucleophile, other than it just having a lot of electron density?
Sometimes lone pairs, or like a Lewis acid or base. It's like a Lewis base.
It's kind of like a Lewis base, right?
Yeah.
Because if we have something like this, and this guy attacks, and takes off. So what is going to happen to this guy's charge?
Increase by 1.
Yeah, increase in the positive direction, right?
Yes.
Yeah. So we kind of have to think not just what is like a general definition of a nucleophile, but we have to think, what do they do in a mechanism, and what happens when you react it in a mechanism? Their charge goes up, kind of like an acid-base reaction. Because effectively, a nucleophile is just a special kind of base. In a lot of ways, they're very similar. Or actually, rather, a base is a special kind of nucleophile. Is that good with everyone?
Yes.
Yep.
Yeah.
All right. So how can we apply this definition on a mechanism level to what we're going to do with the aromaticity argument here?
I don't really know.
Add electrophiles to each of them and see how they react.
Yeah, that's a good one. That's what we could do. So I guess one thing right now, we have to determine the nature of the aromaticity for that. So we're going to do that in a little bit. I might kind of rush through this because we have 3 minutes left. But what can we say? Is this guy aromatic?
Yeah.
Yeah, so Misael says yes. What do you say,
Yeah.
Alex and Moses?
That one's anti-aromatic, isn't it?
So nitrogens are very special because they have this kind of weird thing going on where they have a lone pair so nitrogens are special because they have a lone pair that can either choose to participate in the system or it can choose not to. So it kind of depends on the situation. So if we look at this situation, is the guy on the right aromatic, by the way?
It's aromatic.
Yes.
Yeah, so the guy on the right is aromatic for sure. But the guy on the left is aromatic. It turns out that that's the case. But it's kind of weird because nitrogen atoms, I'm going to try to draw this as like we so the pair of electrons on the nitrogen atom can choose to be outside of the pi system, because one other rule that's kind of true for, or it's pretty much true for aromatic systems, is that they all have to be kind of going in the same, they have to be in the same plane. So that's talking a little bit distinctly from planarity. It's saying that they all have to be aligned vertically with one another. But then these guys are aligned perpendicular to the pi system. And so they're not participating in the aromaticity. But if we look over here,
Let's see, Alex. I think it's about a timeout.
yeah,
Less than a minute.
shoot. Oh no. I'll send you guys a new invite, because I want to finish this problem.
All right.
If we look over here, this guy can either have the H be horizontal or vertical. And so what's going to happen is that because if it aligns the electrons vertically, it will gain aromaticity. It will do so. So again, it's kind of an argument of, is it going to want to choose between aromaticity or non-aromaticity? It's going to take whatever configuration is going to allow it to gain aromaticity. Does that make sense?
Yeah.
Yeah? All right, cool. So I'll stop there, and then I'll start the new